Okay, now that we've learned to look at vectors in a non-x and non-y direction, and then solving them using cos or tan to get the x and y, now we're going to look at that with projectile motion. We're going to advance that piece of knowledge. So when an object is thrown into the air, it's a projectile. So essentially, where we looked at free-falling object, that is a projectile. And there's three possible situations where we throw it vertically straight up and down. We looked at this in free-falling objects. We can throw it horizontally like we do in baseball, or we can throw it at an angle. When we look at objects thrown horizontally, there are some pieces that never really change. And so when an object is thrown horizontally, what we need to understand is that there's a horizontal and a vertical component that need to be looked at individually. And so simply what that is the horizontal is the x and the vertical is the y. So we're still looking at x and y. We're just now using the more in-depth terms of vertical and horizontal. And so they're independent of each other except for time. Time is the same in both vertical and horizontal. This piece is very key. In horizontal motion, we are looking at uniform motion. And when we look at uniform motion, velocity is equal to displacement over time. Okay, always in the horizontal, in this direction, velocity is equal to distance over time. In the vertical, we need to look at it as uniformly accelerated motion, which means that we're now involving gravity. And acceleration due to gravity is 9.81 meters per second squared. And gravity works towards the center of a mass. So if we were to look at a map, I'm not very good at drawing the world, but you understand. Towards the center of the world, gravity is in a downward motion, and that's its positive direction. To do that, we can use any of the 5 vertical acceleration equations. So that's where we're looking for something that has VF, VI, time, acceleration, and distance. When we look at the trajectory, of a projectile, let's look at a cannon sitting on a wheel, and it's going to fire the cannon. So initially, the cannon is there. What we see is eventually that's going to happen. It can't stay in this direction for long. So it has an x velocity, but in this particular moment of initial firing, Vy is going to be equal to 0. There is no vertical movement. Now, as we get here to this point, we still have horizontal velocity, but now we're starting to see some movement in the vertical direction. As we get to this point here, what we can see is that Vx is typically the same ratio. And then as we get here, right before impact, we still have horizontal movement, but now we have great Y movement. It's the largest right before impact. Okay, so we have these different positions. Vy, right off of the initial launch of a projectile, is 0. And then as we move through the process, the vertical velocity gains, but this velocity always stays constant. Now we know that eventually this cannon is A, going to hit its target, or B, hit the ground, and there's going to be no motion in either the vertical or the horizontal. But this is what we're looking at when there's no other forces at play. This is just moving other than gravity. So let's look at an example of what that looks like. An object is thrown horizontally with a velocity of 20 meters per second from the top of a building that's 50 meters tall. How far from the base of the building did the object hit the ground? So let's Bob Ross this. Let's draw our building. A ball is launched from the building horizontally with a velocity of 20 meters, and eventually we know it's going to come to the ground. Okay? We know that this height of the building is 50 meters. We know that the initial launch is 20 meters per second from the top of a building that's 50 meters tall. How far from the base, so we want to know this distance, does it hit the ground? So we have to break this into a vertical component and a horizontal component. Okay, so in the vertical, what do we know? We know that the height of the building is 50 meters. We know that in this direction, right, the Vy, this is Vy, this is Vx, the initial velocity is 0. Right here, right at initial launch, there is no velocity in the vertical direction. The time, we don't know. And the unspoken piece that's at play is acceleration. Now, I wrote an A. We learned it as a G. They're interchangeable. In the horizontal, we know that velocity is equal to distance over time, always, always, okay? We know that the velocity in the horizontal was 20.0 meters per second, and it's asking us to find the distance. And so what do we need from this formula? We have velocity, we're looking for distance, we need to find time. We have two unknowns here. So what we know is that between vertical and horizontal, time is the same. It doesn't matter if I launch it straight out this way, it's going to be, eventually by the time it hits the ground, whether it's traveling horizontally or vertically, it's the same amount of time. And so we need to solve for time out of this particular equation. And so we have D, VI, T, and A. So we need to look at what equation would help me solve for time. And it's this particular one. So step 1, we need to solve for time. Distance is equal to VIT plus 1/2 AT squared. That's the one I would use. We have D, we have VI, we have A. We're looking for T. Now VI is 0. 0 times anything is going to be 0. So I'm not going to worry about that initial piece. D is equal to 1/2 AT squared. So I'm going to move the 2 out of the denominator. I'm going to move A. And then I'm going to remove the square bracket. And I'm going to solve for time. So 2 times 50 meters divided by 9.81 is going to give me 3.1927 and a whole bunch of other numbers seconds. This is not my final answer. I'm not going to delete my calculator. I'm then going to take this time and bring it up here. Know that velocity is equal to distance over time. It's asking me to solve for distance. So distance is equal to velocity times time. And so my distance is going to be when I look back to the original question, I see that it's asking me how far. I don't need a direction. And it's 3 significant digits. For my answer, 1, 2, 3. This 5 will have an influence on the 8. So it's 63.9 meters. Okay, so we're up in our game. We're looking at 2-step problems now. Let's look at another problem. An airplane is moving horizontally with a constant velocity of 115 meters per second when it releases a care package that falls to the ground. If the care package lands in a village directly 1.72 kilometers horizontally from the point it was released, what is the height of the plane when the care package was dropped? First step, draw a picture. So here's my plane. Told you, Bob Ross style. And it's going to drop a package. Here's the ground. And what happens is it's not going to fall just straight vertically. We know it's going to do this. Okay? So they have to think of where they want to go. What happens is they start dropping it here. We know that it's going to land in a village 1.72 kilometers away. My plane is moving in this direction at 115 meters per second. Okay, so it's asking me what's the height of the plane when this package was dropped. So we need to break this down into 2 pieces. A horizontal piece and a vertical piece. So in the horizontal, this formula always reigns. It's the only place that we can use this formula is in the horizontal. We know that velocity is 115 meters per second, and we know that the distance is 1,720 meters. Notice this is kilometers. I need it to be in meters, so I did the conversion right away. In the vertical, I know that my initial velocity is 0 meters per second because it's 0 in the y direction. This is y, and this is x. It's asking us to find the distance. That's 2 pieces of information right off the question. In the vertical, we always know that there's gravity. And so what we need to be able to figure this out, we need one more piece of information, and typically that's time. And so over here, we can solve for time because they talk back and forth. So let's do that. Let's look for time. And when I rearrange the formula, I bring my t up out of the denominator and then I bring my v out. And so I am looking at 115, 1,720 meters divided by 115 meters per second. My time is going to be 14.9565 seconds. That time is now that time. So when I have my vertical and I have VI, D, A, and T, I know that I can solve the problem using VIT plus 1/2 AT squared. VI is 0. 0 times anything is 0. So distance is equal to 1/2 AT squared. If you're going to make a mistake, you're going to forget this squaring piece. So my distance is 1,097.2 meters. When I go back to the original question, I only see 3 significant digits. So I'm going to say that my distance is 1 point, or sorry, not that 9. The 7 is going to have an influence of the 9, which then does influence the 0. 0 times 10 to the 3 meters. Or 1.10 kilometers. You're going to pause it here and you're going to try these questions here. Okay, so we looked at the objects just thrown in a horizontal motion, but we all know that that doesn't really happen. Even when we throw a baseball, we never throw it perfectly horizontal. And so we look at objects thrown at an angle. It has the same idea. We still need to look at an XY component, but we can't assume now that the initial vertical speed is 0. Okay, it is going to have a Y component. And so if we looked at this cannon being fired, what we would see is the ball do this. Because then we get more range. And so right here, at the initial launch of the ball, we're going to have a vertical velocity, and we're going to have a y velocity, even though that's its trajectory path. If we made this relative to the ground, this would be what we call a launch angle. Then we see the ball at this point, or the cannon, not the cannon, the cannonball. We still have the same horizontal velocity. Actually, I'm going to make this a little bit longer. But now what we see is this velocity in the y direction starting to slow down. At maximum height, again, we still have Vx, but now we have no vertical velocity. So that's at maximum height. As we start coming down the curve, we have the same. Notice that we have the same vertical or same horizontal velocity. Now we're starting to gain some velocity in the y direction. And then here, what you would see is a horizontal, velocity, but a much larger vertical velocity. So we have to break the y component down into, we need to look at x and y components across the board. This is what it looks like. An example of an object is thrown into the air with a velocity of 20.0 meters per second at an angle of 30 degrees with the horizontal. What is the total time that the object is in the air, and how far does the object travel horizontally? So let's draw a picture. So here we have a ball. Here's the horizontal. It gets launched, and then eventually it comes back down. Okay? So this is its trajectory. And the velocity at that point is 20.0 meters per second. And this angle is 30 degrees with the horizontal. And so it's thrown into the air with a velocity. When we break it down out of this picture, what we can see is the launch angle, or the launch vector, with this angle. And so then we have Vy and we have Vx. And so Vx can be solved by knowing that this line is adjacent to this angle. So if we were looking at our options, this is the one that we would use. So what I've done here is I've gone the cos of 20 multiplied by the hypotenuse because I want to isolate my adjacent. In order to do that, I have to multiply my hypotenuse to get it out of the denominator and to move it over to this side. And so my Vx then is going to be equal to 17.3205 meters per second. Now we need to look at our y. When we look at it, it is the opposite of this angle, which means that we're going to use the sine. And again, not adjacent, hypotenuse. I'm going to look at using the sine. I said 20, but I mean 30. The sine of 30 multiplied by 20, again the hypotenuse, is going to be equal to my opposite. My opposite is my Vy. So Vy is going to be equal to 10.0 meters per second. Okay, now that I have my x and y piece, now I need to go back and look at my horizontal versus my vertical components. And so in my horizontal, I have (17.3205 meters per second). It's asking me to find the total time. In order to do that, I need to remember that velocity is equal to distance over time. That's the only formula we use in the horizontal. So I need a distance. Vertical, here, my VI is now going to be this, 10.0 meters per second. My A is going to be 9.81 meters per second squared. But we have to think about this. Which way am I launching? I am launching upwards. So my acceleration is negative. When I look at my VF, I need to go back to what we learned when we did free falling objects. And I know that here, my initial right here is going to be the same as my final, but in the opposite. So it'll be negative 10 meters per second. And so in order to solve for time, we know that time talks between both sides. So we need to solve time before we can solve for the distance. So step 1, we need to solve for time. And we know that A is equal to VF minus VI divided by T. If I rearrange it, okay, my VF is negative 10, my VI is 10, and my acceleration is negative 9.81. And so my time is going to be 2.0387 seconds. You should not have a negative number. If you did, you did your math wrong. Time cannot be negative. Now that I have this time here, I can solve over here, which is how far. So what is the total time that the object is in the air? Because I looked from here all the way over to here, this is actually the answer to part A. Part B is asking me how far I go, or how far the cannon goes. And so velocity is equal to distance over time. Distance is equal to velocity times time. So 17.303,205 multiplied by 2.0387. My distance is 35.3119 meters. When I go back to the original question, I have 3 significant digits. So I have 35.3 meters. That's how far away the ball was launched. So you're going to pause it here and you're going to work on these questions, page 145, 9, 12 to 14, and then 18.